Insects are great navigators. For example, desert ants can travel hundreds of meters to find food and return accurately to the nest. Dung beetles could travel in a very straight line, and more like butterflies that migrate over 3,000 kilometers from America to Mexico and back first. At the core of such great ability lies the great use of different cues available in their living environments. For example, the visual cues are factory cues. An insect navigation toolkit containing much mechanisms applied by insects for navigation has been revealed in 2009, but a biological plausible computational model for those mechanisms is lacking. Except the partial integration model proposed in 2017 and some of the visual navigation model. So much is unknown about the visual navigation and its interaction with other mechanisms. In our previous study, we have proposed a computational model that could reproduce realistic behaviors as real ants. The main contributions of that modeling work is 3 building blockers and 2 hypotheses for the neural basis of navigational computation. First is a copy and shift mechanism that could generate desired headings according to the current heading and the presented sensory context. Another is a steering circuit to diminish current desired heading differences. And the third is a ring attract network that could optimally integrate the different cues. One experiment thing of the computational study is that it can make predictions for biologists. So here we infer that the central complex is a navigational center where the multimodal coordination could happen. And the central complex could also receive inputs from other sensory perception regions, for example, the mushroom bodies, for further modulation. So here we ask, if our model could explain visual navigation, how about olfactory navigation? To answer that question, we should start from the behavior. So first, the visual homing is implemented as a gradient tracking mechanism by tracking the visual familiarity. If we adapt visual familiarity to odor concentration, then chemotaxis behavior could be generated. Second, the road following and all the gated animal taxis share the same mechanism as they both drive the agent to a specific direction encoded as the goal. And finally, if the olfactory navigation could be encoded in the same format as a visual homing, then our previously applied ring attractor could also be used here to combine partial integration and olfactory navigation optimally. So we can conclude it here, visual and olfactory navigation share the same mechanism. So here we adapted our visual model to model the olfactory navigation. First is the implementation of the chemotaxis, wherein the increasing concentration of the odor will keep the desired heading the same as the current heading, while a decreasing concentration will trigger the shifting of the current heading to generate the desired heading, thus through the steering circuit to drive the agent to make a turn. We compare our model output with the real lobby behavioral data, and in this specific scenario, we can see that our model agent behaved similar with the real lobby. Then, as the model for the animal taxis is adapted from road following with 2 neural pathways. One is for the upwind direction encoding, and another is for the olfactory processing. It is worth noticing here that the WP neurons just encodes the angular differences between the animal's heading and the upwind direction. So it could provide a signal of the amount by which the current heading should be shifted to generate the desired heading. We also compare our model with real behavioral data. You can see here, when there is no order, the agent just do randomly search. But after the order is set on, the agent just go upwind strictly. And then when the order is set off, again this agent will do random search, such as the real working flight data. And then we come back to ants to model the integration of path integration and of factory navigation using the same ring attractor. We also compare our model's output with the behavioral data, where you can see when the path integration memory is high, the optimally integrated output is dominated by the path integration, so resulting in a high possibility that the agent will bypass the nest that marked by the order. But when the path integration memory is low, and once the agent confronted the order field again, the order information will dominate the output, resulting in driving the agent to the nest. So this comparison demonstrated that our model could generate realistic behavioral data as a real ants here. Basically, we demonstrate how our model could also provide the first account for the flexible changing frame of references here. Just by when the ant is clunching, the desired heading could be generated by the encoded wind direction and then stored as a working memory here to drive the agent back. So what we want to highlight here is these three mechanisms. Thanks for watching.